I brought some stuff which is very, very old, so very low resolution. I was surprised PowerPoint was around more than 10 years ago, so I opened an older than 10-year-old PowerPoint file and brought some stuff which I wanted to make a point, which is a personal opinion, not a truth or barely a hypothesis, but in my opinion, there has to be an anticipation of the technology before the technology gets instantiated. And one of the points that I think comes through with the 4 projects behind us is that in each and every case, the 4 architects were doing something that anticipated digital technologies. In many cases, they were involved in the development of digital technologies, and the digital wasn't something that came, that landed from aerospace in architecture. It was actually something that was developed by the architects in most cases, and in some cases even was developed by the architects and went to aerospace and came back in some different form. So I tried to pull together some things that just show the anticipation of certain digital technologies before they were available in my own work. And I really believe if architects were not ready for computers, but anticipating computers in the 1920s, we would have had them. So I really think it's not a need, but there should be a desire for the technology before the technology emerges. You don't really just receive it and try to figure out what to do with it. And that's a little bit, I would like to make some friction with what I consider to be the received view that architects of my generation went to the top floor of Avery Hall, were given this strange technology, and like monkeys at typewriters started banging on mice until things happened, at which point we started to theorize them. So, yeah, I don't know why, but we're going to see that a few times. Sorry about that. For me, and thankfully my mother didn't save drawings on refrigerators and things, or I'd be showing you even that stuff. But as an undergraduate student, I was required to write a diploma, and I wrote a diploma on Husserl's Origins of Geometry, and was always very interested in the inexact yet rigorous idea of a geometry which couldn't be idealized. This was, when I could draft and draw, but I was already interested in precision, but a precision which couldn't be reduced to some platonic or ideal form. And that came along long before the computer. And since I was maybe 18 years old, I was drafting things with composite curves. I mean, the reason that I went to graduate school at Princeton, one of the reasons was because Michael Graves was there and had been drawing these composite curves for Hanselman House and a whole variety of houses, and I felt a real affinity for that kind of geometry. So that interest, which was a formal and also theoretical interest in certain kinds of geometries, predated the digital for me. I saved these old splines that I had, which were made by a German company, which was a rubber extrusion with discs with crosshairs on it. And they're now so rotten that I have one left. I don't even try to take it out of the case because it disintegrates when you take them out. But I was drawing, even literally as a high school kid, using these splines instead of French curves. And this is an image of what a spline is, but you hear the term spline used in digital technology a lot, but what it really is a series of weighted coordinates, which in some cases you can move, in other cases you can't. But you can dimension points on a drawing, move these splines to those points, and then whatever the material is that makes the curve, in this case it's a wood strip, sometimes it's a piece of rubber or metal, it gives you the curve which passes through those fixed points. And it's something that you can scale up or down depending on the scale of the spline you're using. It was developed by civil engineers and shipwrights and naval architects a long time ago. But the mathematical splines that we use in digital technology are a calculus-based geometry, but they're predicated on this mechanical device. So, I mean, it's just another way of saying that if there wasn't this mechanical device that defines a stream of points flowing through fixed points to make a curve, we would all draw with compasses still. And you wouldn't have the digital spline technology, which was developed for architects, civil engineers, naval architects, not really, and aerospace engineers. Because of this tool, in maybe 80, my dates are going to be a little bit fuzzy, but in the mid-80s, I bought a license of MicroStation by Bentley, which ended up being owned by Bentley because it was a civil engineering package that supported splines. And ironically enough, I still think it's the best spline modeler, just in terms of the integrity of the geometry you get. But so I went towards this geometry because of a drafting tool. The furthest back that I went was the end of the 80s when I designed this really just a geometric exercise for an exhibition that Stanley Tygerman had for all of his young faculty at the University of Illinois, Chicago. And he tasked Doug Garofalo, Bob Somel, Bob McAnulty, Catherine Ingraham, myself, and a few other people with picking a monument and redesigning a monument in the city of Chicago. And I picked the Sears Tower because it was a single and multiple building, because it was the 9 bundled tubes. And I thought, well, I was interested in the concept of the one and the many of Toulouse, and I thought this is very interesting configuration because it's one and many tubes bundled together. So I took the Sears Tower in a site next to Wacker Drive and reconfigured the tower. I did it first with this foam model that I divided into 9 basic tubes and subdivided those 9 into the 25 sub-bays, and even went down to the window volume scale in some places and composed this thing as a physical model. And Bob Somel had picked out an apartment for me, which turned out to be an ex-housing for the blind. So I was in this windowless kind of apartment-fit place where I could draft for 16 free hours a day. So in about 6 weeks, I took this model and fairly meticulously drafted it in pen and ink. And I knew when I did it, it would be the last thing I ever drew, like purely drew, because I'd worked for Peter Eisenman for 5 years, for the Cincinnati School of Design, Architecture, Art, and Planning. We had spent 2.5 years arranging boxes in spline curves, working with our engineers who had the computer technology and working a little bit with computers in the office. And I knew that the digital technology was just about to exceed the capacity of drafting. And I actually think that when I drafted this, it was probably more expedient to draft it than model it, but I knew it would be the end of modeling soon. So I did this consciously as the last thing I would ever draw. So I started off in plan, drawing each one of the floors as a rectangle, and then laid a pin bar over the top of that plan as a section, and drew each one of those plan elements as a section, and then went back to the plan again and picked up the rotation of each one of the pieces in section. So it was an exercise in projective geometry where I was drawing roughly 110 rectangles rotating in planimetric and then sectional space. And And so here's just a couple of those tubes. But they were all defined first in the model, then rationalized with the spline curve, and then along the length of that spline, each one of these was measured and drafted with an adjustable triangle. And in September, we're doing a show at the Art Institute of Chicago, where for the first time, we're putting all these drawings out together. There's something like 36 drawings of all these geometries. But anyway, what's funny is it looked like the computer drew them, although there was no computer involved at all. But it really was, I knew the last thing I would ever draft. So this use of mechanical splines and projective geometry then shifted to a kind of hybrid, very similar to what's going on again behind us, where because of expediency for a couple of competitions that I was doing while teaching at Columbia, I think Cardiff was while I was in Chicago still. So it was before the Paperless Studios had started. And for Cardiff, I got very interested in a book by William Bateson on critique of Darwin. It was all about symmetry breaking and the role of symmetry. And for Cardiff, I came up with this drafting approach to symmetry and mirroring and scaling, very inspired by the biocentrum, if you can see the way that this figure is scaling up and down and mirroring off of itself. So I brought this just because of the influence of Peter's biocentrum project. And this again was done all with mechanical drafting equipment. But then I would guess I didn't spend more than, there were probably 4 people working on this project for maybe less than a month. And we built large models and things. And as we were building the large study models, Ed Keller, who had invested in a Silicon Graphics workstation and a license of Softimage at the time, while he was a graduate student at Columbia University, input that information that we rebuilt in MicroStation into Softimage and did renderings. And these were the very first renderings that I'd ever done, which we did with Ed. And the modeling was all done in MicroStation, but MicroStation had a kind of a shaded view. But anyway, it was the first experiment with textures, and frankly, I would say it got me into some trouble that I'll talk about later. But one of the things that happened after we brought it into the rendering program is we started working more with these, with that translucent fabric, which was never really in the design until we took it into the renderer and started to think about surfaces that would be too complex to draw, let's say. So the massing of this was something which was easily controlled in mechanical drafting software. I could easily migrate it into MicroStation and loft all those spline surfaces. However, the complex spline network of that kind of gold skin is something that I wouldn't have drafted and therefore wouldn't have done until we took it into Softimage. The Yokohama Port Terminal was the first project which was sketched, that I sketched digitally. Again, it was defined by a whole series of splines, the drawings of which I have lots of but couldn't open. But a series of 4 tubes was arranged, kind of connecting all the docking points of the ferries, and then tubes were lofted down those splines. But this was something which was, for me, the first native digital design I ever did. And again, this tubular lofting was something which was kind of entry-level digital modeling, I would say. I think a lot of us were dealing with vivisection and lofts through sections on this project in particular. It was when I got connected with the New Jersey Institute of Technology, which had the first laser cutter in the New York metropolitan area that I know of. And so at Midget, we laser cut this little tiny model, which at the time was like a very exotic and precious thing. Now it's something you do in 5 minutes and throw away. And as well, we started to 3D print with Midget as well. They had a robotics lab that was very important in the early 90s because everybody in New York could use them for stereolithography and laser cutting. I don't know if Peter, okay. But anyway, they had the first accessible machines in their, it wasn't in their architecture department, but it was accessible to their architecture department. They had some special manufacturing facility set up. So anyway, the Triple Bridge Gateway project was done just 6 months before the very first paperless studios. I had invested in a used Silicon Graphics Indigo station, the generation before one of the ones that was in there. It was, at the time, $120,000 new from Lockheed. I think even back then it was something like $20,000. It was a lot of money for me to get. Ed Kettler had one, and Carl Chu had a Silicon Graphics machine for 2 years at that point in the basement of his office in Los Angeles. And Carl was running Alias, and Ed Kettler, as I said, was running Soft Image. I really liked the modeling tools in Alias, and so had gotten the license of Alias that they were giving to me, and had also picked up a license of a software called Wavefront, which was made for particle modeling, particle effects for Hollywood. So I kind of waited and waited. This machine arrived, and a license of Wavefront arrived, and it all came on a Friday morning. And the Port Authority competition, which I was thinking of using it for, was due the following Monday at 6 p.m. So over the weekend, I modeled this thing and turned it in as a competition entry all by myself. And that's just to say that you could not be more amateur in the use of technology than I was that weekend. And what I've always found interesting is almost every concept I've had about geometry showed up that weekend as a problem in this project. So the reason I was excited about it is that the philosophers and theorists that I was reading, including William Bateson's son Gregory, were all talking about vitalism and animation, and I was very curious about the difference between spline surfaces and locating geometry along curved splines that were calculus-based, which I could do in drafting software. And I understood that the animation software was just doing that drafting for me with a different interface. But I was curious about software that was using lights that were meant for rendering as forces that would attract geometries. And I thought, instead of modeling with curves and coordinates, that it would be worth looking at modeling with forces and locating things based on multiple forces in space. And that was really, I had that desire before the software ever arrived. I knew that's what I wanted to use it for. And so I thought the Port Authority Gateway was the perfect opportunity to look at modeling with forces and fields rather than with points. And so the package in Wavefront that I went to was a particle modeling package where you could set up forces of different shapes, all of them based on lights, so spotlights or volume lights or directional lights or linear tube lights. And I kind of quasi-modeled the site with these force elements and then released particles. They came out like these bouncing balls. And tracked the sweep of all of these objects like tracer marks through the site. And just modeled the site up and down 10th Avenue, around the existing bridges, and just started modeling instead of with spline curves, with these quasi-catenoidal curves of these points moving through space based on the attraction of these forces. So it was a different way of drawing for me. I then took curves off of these points and started lofting structural tubes, and then started lofting surfaces that would enclose those structural tubes. And as you can see, all of these bouncing points were intersecting through each other, so I had very complicated enfolding surfaces, where a surface would pass through itself or twist across itself. And I tried to sort that out as best I could in a short amount of time, by segmenting it. That segmenting shows up in the Korean church. It shows up all over the place, this idea of louvering and segmenting. Same thing in the Embryonic House, it shows up. It showed up there as a way of sorting out the problem of crossing curves. As well, there was a tool which would clip curves as they would pass through themselves, which industrial designers call those things webs. And it's called curved loop cutting. And it kept, every time curves would cross through themselves, they would get clipped off, and it was very frustrating. And when I found the setting to turn that automatic clipping off, I found these things called webs, where curves move through themselves, which is also something in the I-beam competition, and various things. I started to play around with the webs as well. So anyway, this kind of modeling in space with forces generated a whole series of problems, which later were thematized as opportunities, let's say. After turning in the competition, we also then printed what for me was the first stereolithography model at Midget, which is this thing sandwiched between these pieces of glass. Anyway, right after that point, the paperless studio started. I have to say it's important for me to always be teaching rather than co-learning, I guess. I mean, I'm always eager to learn things in courses, but I also don't like to learn something along with my students. I don't think that's responsible for some reason. So before teaching a paperless studio, I thought it was important to understand the technology. So that was one of the reasons that I got a Silicon Graphics machine and some software of my own, so I would have a working knowledge of the platform before getting thrown into this paperless studio. And so I could have a kind of strong agenda about what it was that I'd be teaching in the studio. During the time that I was teaching the paperless studio, the first client walked in the door. It was a guy named Joel Citron, and was buying a property in Long Island and was looking to tear down the existing house and wanted to build a new house, was very eager to start getting into culture and was very interested in having kind of signature house, was excited about technology. And around this time, I was starting to use something called kinematics, or inverse kinematics, in this license of alias that I had, as well as wavefront. And it was a way to control the chaos of the Port Authority project. And what a kinematic chain is you can see the points I rendered here just as spheres, that you build a skeleton and you can control the amount of flex in the joints of that skeleton, and then you attach geometry to that kind of lineament system. And you can limit the rotation and change in dimension of those lineaments, and those changes then get transmitted to surfaces which curve or bulge or flex in different kinds of ways. And so in the Citron house, I started using this regulation and proportioning system of kinematic chains to keep surfaces from folding through themselves and to keep surfaces from twisting up through themselves. And as a way of, let's say, constraining the freedom of modeling with forces. So what would happen is various formal typologies. Here's 8 instances of one typology. I built with these kinematic frames and with surfaces, and then would drop that into a site that was modeled with forces and see how it would deform into different configurations. So again, it was using animation software, but tempering it with the different logic of proportion and regulation. About a year later, I got a commission to design a pavilion displaying the use of hydrogen for the OFL Corporation in Vienna. Spent a year bringing this up to construction documents and used that same system of constrained, soft geometry on a site. And in this case, the site was oriented to the Autobahn, and also the hydrogen reactor, really the hydrogen energy system was powered by a solar electrolyzer. And so one face of the building had to be oriented to an ideal solar path, and the other side was oriented to the Autobahn. And so this kind of primitive shape of and the logo for the company is a triangle for the OFL. So this kind of pyramidal triangle at one end, flattened out, and we segmented it and attached each one of those segments to a kinematic chain and started to look at how motion on the freeway would deform it, and then also kind of pin down the south facade to a moving sun at 3 different solstices. So all of the surfaces, instead of calculating the ideal solar moment, we could calculate a range of orientations based on 3 moving suns. And instead of just orienting it to the freeway, it also was deformed to these different tensions of alignment on the Autobahn. And again with Nidget, laser cut this aluminum base and stereolithography printed the models. There were a whole series. Over the year, we did, I don't know, maybe half a dozen or so models like this over at Nidget. So in the kind of history of things, for me anyway, the technology school was more important in terms of the printing and CNC technology than in Columbia. Columbia had a CNC mill around this time that had a bed of 18 inches by 18 inches. I remember Scott Marble, who taught in the Paperless Studios with Hani and myself and Bernard, was really excited. He said, I've got to use CNC table. It's going to change the way we deal with building models. And he said, it just got delivered. You got to come see it. And I was ready to see a 10-foot by 10-foot bed. And it was like this little thing. And it never ran. So I know one of the reasons why I moved to California, I went there, is just for the space for big machines. Because in Avery, there wasn't even space for students, let alone for a big CNC machine. But at Nidget, they had space. Not so many students and a lot of space and technology. Okay, so there it is before we painted it. So that was the look of stereolithography back then, which, for anybody that doesn't know how it works, it's a UV-sensitive resin bath with a table and a laser that moves in 2 axes. And the laser draws in the UV, and wherever it draws, it hardens the resin. And the table drops 1 step at a time into the bath, and you build the model sequentially, kind of in reverse order of a removal process, like a router. So because of all these stereolithography models that I was starting to make, I was asked to do an exhibition at Artist Space in New York. And because of this, I literally became a mechanic for the New York art world. All these sculptors and painters all came and said, I want to use these technologies to make 3-dimensional brush strokes or to make sculptures, or I got connected with the art world in a way that I very innocently was totally disconnected from the art world, but really not at any artistic level, at really the level of like a car mechanic for their forms. The room I designed using a Blob Modeler tool, and for me, that was the reason I started using Wavefront, is because it had one of the better Blob modelers, and Blob stands for binary large object. But it was one of the first polygon-based modeling tools that I'd ever used, and the principle of it is you could take they were all based on spheres. You could take a sphere, which you could scale, and the sphere has a halo around it of influence. And if you bring two of these spheres where their halos overlap, they tear and connect and blend using a mathematics called Chaikin's algorithm. It's the basis of corner smoothing for polygons. Like a sub-D surface is a Chaikin algorithm. But this was one of the first tools that used that. And it would let you model a complex surface without having to always re-loft it. So car designers are very excited about it because if you're lofting surfaces with splines, every time you add something like a door handle, you have to re-loft the entire surface. And this was something I was facing a lot, where with this kind of a modeler, you could just add a piece, and it would be a localized piece on a larger composite. And for me, theoretically, at the time, reading a lot of Deleuze, this approach of multiplicity, where you could have a thing that was whole and add an element to it without having to reconfigure the entire geometric array, was a very exciting prospect. So anyway, for artist space, I started using this Blob Modeler, which had a lot to do also with filleting and radiusing. It's really a way of doing three-dimensional fillets between objects geometrically. And so we built, it was also my first introduction to plastic construction. And my plan was to laser cut this at Midget. It didn't work that they could laser cut this big, so it was 3 or 4 graduate students for a weekend in my office with utility knives, cutting plastic panels that were egg crated together and then skinned with Mylar and backlit. So, that's the rendering and that's the room. And then in there were something like 50 stereo lithography models, all floating. And they were some of the first stereo lithography models that had been exhibited, so it actually made a really big buzz at the time in New York, just because everybody wanted to see what these little microscopic models look like. And it traveled to a show Johan Bettem did in Oslo, Norway, where at the opening, the Norwegians stole every single model I had. It was great. I bought another Silicon graphics machine with the insurance money. But I remember there was a big debate if we needed to put vitrines over everything. We said no. And at the end of the party, every model had been taken by these Vikings. Including like you can see there's a laser cut model of Yokohama, and all this stuff's gone. It's somewhere in like a biker gang's clubhouse in Norway. There's a little model of Cardiff Opera House there. But anyway, and the thing demounted and traveled around pretty easily, which also became a kind of preoccupation of mine with plastics, is the ability to disassemble, pack, and reassemble them. Okay, so in my mind, all of that work was about surfaces, and it was very driven by the use of animation technology and the ability of animation to iterate an element along a path or array elements along paths. And I started to migrate towards a very tectonic approach to digital technology, which I would say is now very much au courant with parametrics, where a conventional method of construction by frames is put through a digital logic of iteration, transformation with each copy in space. where every element became unique and every angle became unique, and it was really an expression of frames that were clad. And the first thing that was using that logic of a kind of animated frame was this temporary installation I did at the Secession Museum in Vienna with Fabian Marcaccio, which Jeff Kippis ended up calling the Tingler, based on the Boris Karloff film, or the film from the 1960s. And this was all aluminum extrusions, which were computer cut and then manually assembled. I forget the name of the contractor in Austria, but at the time, fairly sophisticated digital contractor who built most of Kurt Himmelbau's work, including rescuing BMW World from bad German steel contractors. But anyway, it was a kind of Austrian metal fabricator that did all this in aluminum, including this frame on the outside. The Fabian had a plan for printing large-scale prints, which actually didn't work out here. And a few months later, we were both asked by the Wexner Center to travel this to Wexner. And we actually said, yeah, we'll travel it, but we'd like to fix it. And in the 6-month duration of fixing it, we completely redesigned it, which I'll show you what that is in a bit. You know, that approach was the same time that I started designing the Korean Presbyterian Church, which in a similar way uses spline surfaces as controlling geometry for frames which iterate with every bay, and so every structural member is a unique dimension and every angle is a unique angle. And the hope is that out of that sequential change of tectonic elements comes some dynamic space, which you know, is not a smooth surface, but has the qualities of rhythm and direction that a surface would have, only through a logic of tectonic construction. And this, at the time when Doug and Mike and I designed it and did the construction documents, we couldn't, with Burrow Happold, who was a structural engineer, we didn't have access to X-Steel or a program like that. So we, in fact, had to do every steel detail and wrote some custom-built scripts to help us do some of those details. It was fairly labor-intensive, or now it wouldn't be. Anyway, but so that foray into tectonics, I would say, kind of, I shifted back to surfaces. At the time, a lot of journalists were looking at my bad computer renderings, like that Cardiff Bay rendering, and there seemed to be an assumption in the journalistic community that anyone using a computer should be building smooth, unarticulated surfaces and plastics. And my reaction to that was to build highly articulated frames in metal. But frankly, I really did want to build smooth, unarticulated surfaces in plastics, it turns out, in composites. And one of the ways to do that seemed to be through CNC machining, like, let's say, subtractive machining. And so what became the Predator, which was the Vienna Secession installation, moved to the Wexner. We ended up claiming that it was too expensive to ship it or something, we should just rebuild it. But really what we did is I used half the budget and bought a CNC mill for my office and started to make all of the molds to build this plastic shell. So this was 16 years ago I bought this machine. Actually, it's been rebuilt a couple times, but still, you know, we use it all the time. And what I did was build foam molds to build a vacuform plastic shell that was made by Warner Brothers. And this, when I did this, it was in the first couple of months I moved to Los Angeles from Hoboken, New Jersey. And so you know, this kind of figure is something I designed with Fabian, who's a painter. And the idea of it is that it had some of the qualities of a lot of his digitized brush strokes, but it was given three-dimensional volume. And you can see some of the studies of it in 3D that we did. And we started vacuum forming on molds to make the physical models. And in doing so, I started to, instead of building the surfaces all smooth, to program the path of the tool to give the surfaces a texture and pattern. Fabian also had digitally painted the surface of this and found a large format digital printer used for Hollywood sets that could pre-print the PET plastic before we would form it. So it was a kind of physical image mapping where a painter's decoration, along with the path of the tool that I'll show you ends up becoming decorative as well, was all put into this surface. So here you can see the relief of that painting as a texture. So we relief mapped images onto the surface as well as printing images on the surface, and unfolded this thing. Each one of those little chips is a 4-foot by 8-foot panel. And we digitally printed all those panels above and then took them to a vacuum former at Warner Brothers, and they three-dimensionally formed them. And then the panels were shredded with this kind of louver system, like I was saying, was in Port Authority. And actually, very much in my mind, this is working out that Port Authority massing in a lot of ways. So anyway, that was then shredded out and then formed, shipped to Columbus. Jeff Kipnis honchoed the construction and called me, and I was going to come 2 days later. I got out there, they would put it together inside out, believe it or not. So I had to take it apart and put it back together right side out. But you can see that there's a texture that came from the tool, which has the relief of Fabian's paint diagrams on it, as well as a kind of corduroy texture to give to make the joints go away a little bit. And I was spending a lot of time with automobile designers and realized all those straights and lines and things are to make the panels of a car go away. So you can have a really badly built car with big gaps if you have big creases that go across all of it visually. So anyway, and it was a thing you could walk around in, and was three-dimensionally painted and printed and textured. That approach to surfaces, then I didn't bring the Clyburn plot, but the animation tools I realized, and again, this was a little bit from concepts of what you would call a primitive instead of a typology. And again, it was coming out of 19th century texts, or texts from late 1800s on thinking through typology and biology. But this term primitive and variation was a thing that I'd taken from William Bateson and started to model geometrically, again with this system of constraints like the kinematics. And the first place it really worked was in the design of these coffee and tea towers for Alessi. And Alessi commissioned 25 architects to design coffee and tea services on the 25th anniversary of the postmodernist ones, the ones where Venturi and Meyer and Graves had all done these coffee sets. And one of the things I really enjoyed, actually, Alberto Alessi's brief. What he had were these rules. I forget all 5 of them. There's 5 rules, and if you satisfy 3 of the 5, you'll be successful. And if you satisfy 2, it'll be a failure. And the rules were things like it could be unusual, meaning something nobody's seen, like that you'd be curious about. It could be elegant, meaning that it could be kind of small number of parts that were well integrated. It could be cheap. I'm forgetting the 5. But some of the ones he showed, like the Philippe Stark lemon juicer, where he said, well, it's cheap, it's unusual, doesn't function. That was one thing, works. Doesn't function. He said that everybody looks at it and they say, what's that? And they say, oh, it's a lemon juicer. They say, how much is it? They say $9. And they sell 2.5. Every purchase of the lemon juicer by Stark is, they typically buy 2.5. So you say, like, I'll have one for me, and you know, my niece is getting married, I'll get one for her, and I'll get another one. So anyway, he gave us these rules, and he said the one thing that architects never do when they work for a lessee is they don't put handles on things, because they like everything to be pure. He says, make sure to put a handle on it. So I had this idea to make a coffee set that was 100% handles. So the idea was that you would want to grab this thing in different ways, and that the gripping locations would determine the shapes. And then I had an idea about how it would get put together, that there would be 2 surfaces on the exterior that would be the grip surfaces, and then there'd be a flask on the inside. And the 2 things would be separated thermally. So you could grab it anywhere. And then out of that, I came up with a family of curves which were sympathetic to each other, meaning if you lofted from any one curve to the other, it wouldn't fold through itself the way the Port Authority surfaces did. It wouldn't have a crease or a seam. But the transition from one curve to another would give you more or less a nearly ruled surface. And the idea of those shapes came primarily from how you might grip it. So you can see there are 8 different curves in that family. And you can see a grid of the 8 vertically and a grid horizontally. And then when you loft from any one curve to another, you get a certain kind of figure. And this was the first time I ever wrote a parametric tool. At the time I used Microsoft Excel. So, because you could easily plug Excel into what was then Alias. So anyway, there was this family of curves, and some of these, like this is a really big container. This would be like a big coffee container. You can see in red that it has 5 curves. So you could have 8 options in 5 combinations. So, you know, we were getting up around in the tens of thousands of coffee pots that we designed using this parametric approach to the curves. So, you know, we ran that. We had the routine to run all of them, and then just started picking from within that space and manufacturing with the mill different options. And so you can see, you know, here's some of them. I mean, there are literally hundreds of these that we made as solids, and started figuring out when you put the ones together, what kinds of configurations we wanted. So this was really exploring a system where you would design the tool and design the system, again, knowing what you wanted to get from it, more as an expedient way of giving you the variations you wanted, rather than as some kind of like monkey and typewriter experiment. So anyway, and then the plan was always that I would give models to a lessee, and their team of artisans would hammer sterling silver into the shapes that I gave them. And I said, well, look, you gotta have this texture on them. They said, that's gonna be a big problem. And they said, we have $70,000 to do it. And I think this is going to cost more than $70,000. I was like, $70,000. So I went back, and this was before the web. It was in Yellow Pages. I looked in the Yellow Pages for titanium superformers, and I found 3. And I called the one called HighTech Welding. And I said, I got $70,000 to make 5 coffee pots. They said, no problem. So anyway, I think they regretted that. But But so you could see the way the titanium was formed is very exotic. But we did mock-ups in plastic, in vacuum formed plastic. So these are kind of inside grip surfaces. Those are the reversible trays. And we cut all these things with the mill, molded them in plastic, you know, painted them with the gradient that we wanted to have, and went down to HighTech Welding and showed them what we were after in terms of the grip surfaces. And then, you know, they then took that geometry and cut with their own mill out of graphite, and then they would weld together pillows, like 2 sheets of titanium as a pillow, put it in a mold of graphite, put it in an oven, pump all the oxygen out, because it has to be 0 oxygen or you cake oxidation when you heat the titanium. Then they heat it to 900 degrees Fahrenheit and inflate it. And then once it's inflated with argon gas, they put a little bit of oxygen in and light it, and it explodes into the mold. So you get this really high resolution texture. And then it's all welded, and that's how it comes out of the molds. And then it's all cut and welded with a robotic arm so that you don't build oxidation up when you're welding. So super high tech, costs $4,500 a set, and we sell them at $45,000. So really great profit margin for a lessee. But it was the first thing I did that was what I would call surface minimal. And surface minimal, I mean that the hardware and handles and articulation was all integrated into a curved spline surface rather than adding attachments. And for me, it was a real revolution in thinking, because I had been, like with the Korean church, going towards a tectonic complexity where more elements with more difference seemed to be the direction of digital tools. And I have to say, when I started, I was thinking of compound curves and knitting things together with curves and fillets into continuity. And the digital technology was giving me that, but the construction logic of frames was pushing me towards this, what I would call now, I would just use Patrick's term and say a parametric approach to arrays of high degrees of complex elements. And you go to an Alessi or a Vitra or a car manufacturer and you say, hey, great news, I've got this amazing technology. You used to make a chair with 8 parts. Well, I can make a chair out of 10,000 unique parts. They look at you like you're retardataire. And I said, that's not innovation. That's just ridiculous, you know. Make a chair out of 3 parts, and that's innovation. And it really, in every industry but architecture, the impact of digital technology is the elimination of extra assembly, the elimination of extra components, the integration of more function into fewer parts. So for me, this language of surfaces let you do what you would have needed a handle to do with a surface that was also the legs and the support and the tray. So it really was a shift for me moving towards a logic of curvature which was not controlling frames and panels, but a logic of curvature which was integrating function. And for me, my focus is towards making surfaces kind of high function, high performance, minimal component. So this was the first thing that was that way. We'd forgotten to make a tray, and you know, we sent some photos and they said, well, hey, you need a tray. And so the tray we made is reversible. So the legs that it sits on, let's say, become the grooves that you can lay the thing open on when you display it on your coffee table. So when there's no liquid in it, it's like this flower with the tray reversed, and then when you actually use it, you flip the tray back over and then it all nests in and stands up. So again, even the tray has this kind of functional performance to it. Okay, and then the last thing I'll show is one current addendum. is the Embryonic House, which was really precipitated out of this Alessi project, where I thought, well, you know, if I can design 10,000 coffee pots with a network of curves, how could you think of a house which instead of, well, which would be perfect because nothing could be added or subtracted from it? I thought, what if I designed 50,000 houses, all with exactly the same number of components? And what if instead of doing this tectonically, it was really more like a shell? So the Embryonic House was starting with that approach that came from that curve network, like a sympathetic curve network, and instead built that network out of something which would have, you know, which would give you the volumetrics of a domicile, where nodes of it, which these are where those blebs came in, would fold out and start to make kind of quasi rooms. So it's a one room, they're all one room volumes, but those rooms are surfaced in such a way that you start to get pockets and niches, let's say, that subdivide the space. And here, I forget the number, it was close to 60,000 that we actually did run through and geometrically model and, you know, build from little tiny stereolithography to slightly larger CNC molds. And really, I was trying to turn my office into like a house factory at this point. I mean, it was just like, keep cranking out the embryological houses for 2 weeks. Let's see how many we can make in 2 weeks. And so, you know, we did hundreds. Phyllis Mirko can attest, because they're in the basement somewhere, of sizes from, you know, something that would fit in your hand, that could be made with 2 panels, to something that got slightly larger, again, still with 2 panels, to then things that were approaching the actual construction concept of the house. About to get bigger there. So this is now, those are the surfaces of 3 different houses, filleted. So divided into strips, and then those strips broken into panels. So, but then lofted together as a single surface. And again, this was all done with, this was now Maya, probably, and was all done through scripting. So we could take a volume, well actually we would take curves, send that into Microsoft Excel, write a script, plug it back into the software, and get our 50,000 volumes. Then each one of those volumes you could drag, and it would then subdivide into the panels, lay the panels flat based on 3 maximum points, and then loft across the whole set. And then we would take that into our router software, and then cut the molds. And then we'd vacuum form on each one of those. So the mold for each one of those volumes is what it's sitting on right now. So every one of those panels is in the surface. We vacuum form it, cut it out, and assemble them. And we did maybe 6 or so of these larger ones. And then we did a couple of real big ones. Where here now, each one of those kind of 3x6 panels is making maybe a 1/12 of the house. So then they started to get really big, kind of dog size. We did a few of those. And then for the Venice Biennale, we went really huge. And did this giant blue thing. Oh, we also were laser cutting. The idea was that there's a kind of shade photovoltaic structure. We did some 3D printing of them, kind of thinking about the bleb effects as they would move out into the landscape. Then this giant thing, which you would think foam doesn't weigh anything. I mean, we just said, oh, we'll cut it in foam and hang it on the wall, and we got a call called and they said, okay, we're delivering it, it weighs 2.5 tons. So, foam actually, the 1 pound foam weighs a lot when you get a big volume of it. But so this approach to a surface that integrates fenestration and structure and envelope and that subdivides based on folds, just to see how it shows up 10 years later, even though it's not an egg. In the Bloom house, all of the volumes on the ground floor are modulated by folding curved walls and surfaces. So here, the clients wanted something with the character of a loft in the sense that it would be a one-room living space, but they wanted it to be cozy and not cold. And so I was thinking about the embryological house volumes where one room gets subdivided by these kind of pockets and folds. And instead, this is a room which is, divided by curves and pockets, and all of the equipment, like the fireplace and all the kitchen equipment and the bathroom fixtures and everything is all integrated into the walls as surfaces, very much like the OSI surfaces. So this logic of something which fillets and curves as a way of incorporating multiple elements into a single surface was really working here in terms of a wall which continuously rolls along the whole room, but folds and pockets to make these different rooms. So there's like a little breakfast nook in one pocket, and then the pocket makes a little home office, and then folds around and makes the stair. So every one of these surfaces is undulating to make rooms without making rooms that are really volumes, but more spatial crevices or volumes. So, and then I'll show you one last thing. Inanimate form, which was trying to think through the use of animation tools as design tools rather than literal moving things. I made an argument where I didn't say things could move, but I just said to use animation to its best effect didn't mean the building had to move. And recently I've gotten very interested, a lot because of what Peter's been doing and because of what's going on with the late Mark Fisher, in the spectacle of motion and how the spectacle of motion could get scaled down to, let's say, a more everyday scale. And I was asked for a construction fair in Belgium to do a very small house, and decided that the best way to do a small house would be to roll the surfaces around so you could use your walls to live on when you rotated your house. And we built this 1/5 scale model of the house and built the robotics for it and programmed the robotics for it, and even did some smaller models where we 3D printed all the gimbal furniture that would roll around as the house moved, as a way of thinking about literal motion and form. And so kind of just to close that loop of animation tools, 15 years later or 20 years later, I'm kind of cycling back to a lot of the same themes in terms of surfaces which are ergonomic and high performance, but now looking at how the surfaces can move and roll and do things that you couldn't do with a tectonic frame. So that's it.
This literal motion, you've done quite a lot of work with that in addition to the project you're showing. Could you talk a little more about where you see that going, what your real interest in that is, where you imagine taking that?
you're asking me to preempt tomorrow morning.
Okay.
That's why I have a whole plan.
Okay.
I don't want to do tomorrow morning now, but I would say that architecture's timeliness, like its relation to the contemporary and its relationship to being timeless or permanent, for me, it's something really worth thinking about. In your talk this morning, I kept thinking about it, like if you were a designer at Nike presenting the tower, the questions of meaning and relevance, they would come through very different if it wasn't architecture. And I think there's an expectation because of the longevity of buildings and their relation to the contemporary and their relationship to memory in the past. There's a different kind of expectation put on. So, but the way you said you don't talk to those people that don't use computers, I'm starting to think I don't want to talk to those people that are doing that job. I'm kind of more interested in the person whose car drives itself. What do they expect out of their office? So, or the person that works at Facebook, what do they expect out of their office? And I think architecture can start to engage that level of contemporary technology in a way that's not just about spectacle theaters in Vegas or U2 concerts, where robotics really is now in architecture in a very serious way. And I think if you look at Rem's work and Liz's work, they're all really thinking about motion and robotics now in a significant way. But it tends to be more for cultural spectacle. And I'm curious more subtly how motion might start to show up in buildings. So anyway, I think that's a place that there's a lot going on with the intelligence of everyday objects like cars and phones, and you just have expectations about your environment having a relationship with you that I think architecture can start to enter into by using motion. So everything from putting motors and sensors on furniture and just being able to park it with your cell phone and roll it out when you need it, and having it be smart enough to know to roll away when you're not around or roll out at a certain time of day. I think that's just going to become more and more relevant.
So you see this at this more intimate scale than, say, the Diller's video, a huge structure, or do you see that as also?
No, both. I think it's all part of the same interest in motion right now. And if there is it's really not even the immediate future. If there's action in architecture right now, that's where a lot of the action is. It's in moving, getting things to move, and getting them to move in a not a gratuitous way, but in some, contextually specific or functionally driven or experientially driven way.
So, and I won't be here tomorrow morning.
Yeah.
I don't want to preempt it, but how do you see that different from, say, in the 60s, that the interest in moving and architecture from that period?
Not so much. I mean, not too different than Leonardo or the 60s, right? I think architecture's always been...
Because that's been something out there, right? Is it that we have another way to do it now, or?
Well, once you move something, you start to see everything in a different way. The number of components of a building that move already is pretty high. So it's more just a question of doing something more with a door than just having it open and close or, I really think that that's where, also in terms of, speculative work that we're doing, and also work at UCLA and Vienna, that's really what I'm looking to do is figure out how to how to rethink everything that already moves in a building, plus a little bit. But yeah, I mean, the rolling around building was really more for us to make sure that we had the skill set to program it to move. And it's up at Facebook right now, and they're writing interfaces to move it. from Facebook and from devices. And when we get it back from Facebook, we're going to start to put some sensors on it so when it moves, it doesn't bonk you in the head if you're standing next to it or swing around and knock you over. And once we get that, we're also, for the new lab at UCLA, all of our conference tables will drive. So, because you can't really kill anybody with a conference table, so we figured once we get the conference table so they're smart enough not to hit anybody, we're putting the faculty offices on beds and driving those around. So we can just start to like live what we preach and see what happens when your furniture and rooms can start to be reconfigured. I mean, it's what you do anyway in a school of architecture. It's just usually it takes 3 people pushing things around and rolling television sets for reviews and all that stuff. We're just going to try to put a little intelligence in it and make it part of the design.
Well, that's fascinating. In relation also to the Facebook headquarters firm, is there any potential to interface with that on the equipment level?
Yeah, that's the plan. Because Facebook's got to be a one-room building, so you need kind of big furniture.
No, that's very interesting. Also, that space. I was curious how you guys were going to occupy such a huge space.
Yep.
So that's really interesting.
One of the things I was struck by with your drawings up front is that actually your drawings were done without computer, but they themselves are computers, the work and the set of, I don't know, processes that you were going through. I don't know if it's really a question, maybe it's a comment, but I wonder if computation has had a longer, broader role in your work than maybe an archaeology of your own archaeology of the digital.
Well, curves, for sure curves. You know, I was always drawing curves that were anticipating spline surfaces and networks, that's for sure. I think in terms of primitive elements that get arrayed, no, that came straight from digital technology. I mean, that's something that I saw as a potential and then connected with concepts. And, you know, it was a library, honestly, that triggered it. I mean, I remember the afternoon in Chicago when I went to the Chicago library wanting to do some research on variation. And I went to the card catalog and found William Bateson's book called Discontinuous Variation as a Critique of the Origin of the Species from 1893 or whatever it was. And I thought, oh, this looks like an interesting book, and I wondered if he's related to Greg Bateson. And so I grabbed it, and you know, that was where the concept of the primitive and the concept of symmetry breaking and all that stuff came from a combination of early digital tools, drafting with curves, and concepts, you know, theoretical concepts, and they all just kind of fit. But I mean, I really think that's how technology and innovation works. If you're missing any one of those components, either a preparedness technically and an anticipation of the tool technically, the tool's not going to get developed. But I think as well, you also need the theoretical concept and some idea of how to implement it in your field. Otherwise, you don't get technology. But I do think it's too simple an idea that you get high technology from another field and play around with it. I mean, the term experiment got used a lot at Columbia, and I was always like, this is like some kind of art project or something. Like, an experiment has a hypothesis and judgment involved in it somewhere, and there was a lot of things which was just like, you know, blowing particles and coming up with base drawings. I guess that's actually, you know, before the paperless studio, I was doing a lot of reviews at Columbia while I worked for Peter, and there was this base drawing phenomenon where everybody would just trace palimpsests of stuff until it was such a mess that it was not just a field, and then everybody would edit that into extrusions and volumes. And it's amazing how, I remember when Bernard taught his first and only paperless studio, he said after the first day, these computers are amazing, they work in layers. So he was really excited about the ability to scale and orient layers like a base drawing, and then edit out of that context into form. So again, it was there before the digital technology was there, and then the digital technology just opened up some other path.
I had a question related to paperless studio, because you evoked several times the paperless studio, but now you didn't get into the story. And so I wanted to ask you if you can comment upon the maybe the first semester in the paperless studio, because you said you built the machine in order to really understand how then to teach about it. And so I was wondering which were the first kind of the pedagogical terms and instruments that were used in the studio and so forth.
So I have done, in the kind of Texas Ranger style of the 9-square grid, I had come up with this pedagogy I used to teach called the potato problem, where the first day of studio, I would come in with the number of potatoes, one potato per student. And I would say, look, if we were interested in spheres, you could all just take this potato, measure it, and draw a sphere of that size and be done. But we're not doing that kind of geometry. What I'd like you to do is measure the surface, be able to reproduce it, then I would collect all the potatoes, then they would build models based on their drawings, and then bring it back out again and match them up to what they did. But it was a way of getting kind of surface geometric intricacy with curves. And I've been doing that for several years. In the first paperless studio, I just taught the potato problem with spline modeling software. And also with curves and fillets, some people did. But so I took a kind of existing pedagogy, which I have to say I developed the potato problem because I knew I had spline modeling tools and the students didn't, and it was a way for me to be engaged and interested without them having to have computers. But so that was really my approach, was pedagogically to pick a very focused set of techniques out of the paperless studio equipment and focus on that. I actually don't remember what sites and what brief I did. I don't even remember how many paperless studios I taught. Probably they weren't around that long, and there was like the paperless studio for maybe 4 or 5 years at the most. And then pretty soon it was just, the equipment was just all over the place. The other thing that was important was the students that initiated it. It was Ed Keller, forget who else. Students started to, I don't know how, buy these really high-end silicon graphics machines. And they started to show up around the school. And it was really Bernard who saw that happen and decided to make a commitment to it as an institutional thing. But other people taught it in other ways, and I think we should probably, my memory does not serve me well enough to paraphrase how they approached it. I remember Bernard's thing about the layers really vividly. I know Scott was really interested in hooking it up with manufacturing. So, and Bill Massey was one of Scott's students then, and Bill and Scott were the two that bought the miniature CNC mill for the basement. But I remember that was his interest, was really more towards manufacturing. But anyway, it was a big shift in pedagogy, that's for sure.
I wanted to ask you about this relationship between the smooth and the fragmented. I think it was like in the late 60s, Derrida said that coherence in contradiction expresses the force of a desire. And I've always been interested in this approach of trying to not only your work, but the work of other architects also in the 90s, like Alejandro, for example, the fact that there is this apparent contradiction between the smooth and the fragmented, which expresses the desire of the possibility of understanding space and form dynamically rather than statically. So, I mean, that's maybe a too elaborate way to just ask you how you felt at the time of having to fragment your objects and your projects, where when it seems like your real desire was to actually push in the direction of curvilinearity and continuous surfaces.
Yeah. Well, for me, I think and I mean, I could do a 180. I mean, I've done a 180 once. I could do it. I hope I do it again. So I don't think there's any truth to any of this, but the disjunction between structure and geometry that happens in composites primarily, but that's happening now in building construction is it's a very big idea for our field. So, and what I mean is that when I was modeling something, I always thought the lines that were defining the geometry would naturally be the center lines of structure, just because that's how it's always been. You would lay down blue lines and then put columns down, and that would become, the lineaments would become the structure, and then on the structure you'd start to make enclosure and cladding. Well, if you make a boat, for example, the shape is driven by how much interior you want and performance and precedent, all kinds of things, but not by structure. The structure is, you put it through finite element analysis, and where you need more structure, you put more cloth. And where the loads are in a particular direction, you orient the cloth in a particular direction. And so there's the form, and then there's the laminate schedule. But the structure and the form are completely unrelated. And that's a really big idea. I mean, you see it, unfortunately, in the bird's nest, the structure gets duplicated. And in CCTV, Seattle Library, there it gets interesting because the finite element analysis of the structure just adds some layers. Just like you would add layers in composites, just doing it with steel. And that shift is a big shift. It means you don't have to design everything structure first. The structure can come later. And I don't really think that's even started to play out in architecture yet. I mean, it's a very new idea, it's a very big idea. I think people have backed into it. I mean, people don't even realize that's really the paradigm that they're dealing with in some of those projects, but it's a very significant opportunity to do something with. So for me, that's the real thing, is just not always making my geometry into structure. And that's my problem with Patrick's theory of parametricism, is that it just says all geometry is structure. It's primary structure, then secondary structure, then cladding, but the lineaments of the geometry always become built as elements, rather than just saying the volume is the volume, and the panelization and the structure is just the panelization. The structure doesn't have to follow every isoparm and polygon.
So you're saying that in a way to fragment and otherwise continuous surface, basically we're interested in exploiting that in terms of this disjunction between structure and space.
Exactly. Yeah, it's not a one-to-one relationship.
So projects like today, for example, Toledo Station Opera, where structure and space are the same thing, I mean, that's kind of the intention, and yet here achieves a high degree of complexity there. And that's actually not interesting to you in that sense.
No, it's actually very, I find it very crippling. I mean, I find that desire to make a monolithic surface, structure, volume design. I don't know why. I mean, I don't know what that concept is. I don't know where that concept comes from. I can show you a lot of really bad buildings based on that concept. I mean, probably some of Toyoto's worst buildings are based on the concept of a monolithic single surface expression in a typology that makes a single surface expression impossible. Like his building in Fukuoka, I mean, not to like, look, everybody's got good buildings, great buildings, and not great buildings, The Fukuoka building has a diagram of a single surface, but the typology is of a shed. And I mean, it's just so frustrating when that single surface has to hit the vertical structure and hit the floor, because it's tortured into an expression it just can't make. Where to liberate that would be so much easier. I don't know where that desire for monolithic surfaceness comes from.
Greg, when I first knew you, you were very much involved with Darcy Thompson.
Yeah.
And how did that play into, into the reading of the later?
Yeah. Well,
What was it called? Structure and form?
growth and form.
Growth and form.
Yeah, pyramid growth. Well, what I saw in it was a deformable grids. I mean, it was a purely visual thing. Was in the Darcy Thompson, I saw the deformable grids. Same thing in Muybridge and Murray. I saw the iterating sweeps. And so, you know, fundamentally, I was more interested in as a visual structure, as the deformation, than as a, let's say, what Darcy Thompson was really about, which was categorization and typology. I mean, like as a set of ideas, I mean, you know, it doesn't really matter. The ideas of Bateson, to me, were always much more interesting than the ideas of Thompson. And then it's a really fundamental debate, but it's geometrically, there's no difference between the two. But so I always loved the Darcy Thompson geometric transformations. But then was always embarrassed when I would meet a scientist who would spot me with the Darcy Thompson diagrams because I knew the ideas were wrong. But the deforming grids was something I spotted and thought, those look like splines. And they look like splines that are deformed based on a field, which was, you know, that's Thompson's argument, is that performance, you know, a fish that needs bigger eyes, he would deform the grid and the eyes to show that that was a measure of the performance of that particular fish. So the idea of a performance field and a deforming grid was something that I thought was really a kind of interesting geometric concept. But it is true, I mean, in the history of all this digital technology, there was a particularly British trend towards justifying things as natural. And Charlie Jenks was key in that. And actually knew all, you know, Dane Farmer and everybody at the Santa Fe Institute, Charlie was really connected with. Oh yeah. And there were a couple conferences at the AA and also at the something like the New School, the London New School. Anyway, Charlie had 3 or 4 very important conferences where scientists were brought in, you know, more physicists actually than biologists, who were looking to justify things as natural or organic. And there was a lot of sleight of hand of, you know, that looks like a leaf, so it must be good because it must be natural. So, I mean, at a very high computational level, things were going on, but then judgment was being rendered in a very kind of funny way, visual way. So, and I think my interest in Darcy Thompson was probably part of that whole phenomenon. But in writing the history of the digital, I think it's important to take in that British, you know, Santa Fe Institute axis.
Thank you for your lecture. As an introduction to my question, I would like to say that I like most about your work is that I think it's very original. That the things that you do and that you show us have never been done before, and that you could actually have done those without using the techniques and the technology that you developed and that you use in order to develop. And I think that you synthesize this very well when you close your lecture saying that you do things you could not do in a tectonic frame. So this this has been said, I would like to go to the project before the last one. It's called the Blob Modeler.
Yeah.
Which I think is a very interesting project within your work, exactly because it's a house. And I would like to ask you from the point of view of the user, if what you deliver could not be done and delivered within an Embryonic frame.
Well, the cozy loft quality, sure, you could probably interpret that tectonically. But in the occupants, it's a slightly complicated story because the owner ended up marrying a woman who started designing the project for him, and now two of them live in the house. So she kind of designed it for herself, so of course she loves it. But I do think the surface expression is very much part of the house. It doesn't photograph so well, but when you're in it, it feels spacious and intimate at the same time. And part of it is because of that glowing lantern. It kind of brings the scale down, but it also glows, so it doesn't feel claustrophobic, but it is claustrophobic. So, but I think that the surface has a lot to do with it. I mean, there is a tectonic frame. I mean, there's a lot of tectonic, steel moment frame in it. But then also a lot of it is all built out of egg crate plywood and built in plaster and lath. So I think the smoothness is definitely part of the smoothness and undulation you couldn't take away. But I mean, look, I don't think this is a personal approach to the technology, and it's there's lots of things you can do parametrically and tectonically. But I don't think there's an ideal spatial idea that's detachable from the design technique or the construction technique. I think spatial quality comes from the construction and the design software. It's not an ideal detachable thing. And I also like to think that it's a contemporary expression. I mean, that it's of today. I mean, to me, it's really important to try to do things that are relevant for now, rather than relevant for the future or relevant for the past. So, I mean, I think tectonics has had a good 2,000-year run. Maybe it's time to do some things with surfaces. It doesn't mean tectonics are illegal. I think it's just there's a niche for surfaces.
Sorry,
I'm quite intrigued by you. You have always, in your career, you have always had an interest in motion. It's been through your career all the time, especially of course in the last project. I'm wondering if there's a kind of line of rhetorics from which the information that moves the object comes from. Because beyond ergonomics, like a window would, or like a door that's just ergonomics that moves the door. That kind of information. I'm wondering if you have kind of this agenda behind that, or there's a kind of a position that goes beyond just the ergonomic properties of the object.
Well, I mean, it's there's definitely a Baroque, like a full-fledged concept of Baroque dynamic space that I've always believed in. That you would view a room with an orientation and character that has a dynamic building to it. That as you move through it, you experience. And I also think when I first started using surface modeling, I was really like sensitive, like hurt that people would say, oh, Lynn doesn't care about interiors. And I remember I got that everywhere, like with the Korean church, everybody said, well, there's no interior there. And I'm like, the whole thing is there's no exterior there, it's all interior. I've always been very inside out concerned about design, like whatever the internal volumetrics always drive the volume and the massing. And so for me, I think a kind of Baroque sense of volume has always been a driving thing in terms of motion. And that, I would say that's a constant. But a focus on ergonomics or I'm designing now, working on co-designing some boats with a naval architect who's in the office full-time. And that we're using computational fluid dynamics and finite element analysis and like the real version, it's not real versions, a more tested version of the kinds of things we were playing around with wavefront in the 1990s. So instead of blowing particles around and shaping something based on kind of loose idea of a context, now we're like running high-level surface tests of fluid dynamics on boats that go through the water. And that level of kind of pseudoscience is also something I'm interested in, but it has no architectural consequences yet. I mean, we'll see if something from that high-performance boat world migrates into architecture. I'm sure it will. I'm doing it more for the construction logic of the composites, but I think the design tools there are super interesting, and I don't really know what they'll do in terms of architecture. But
can you just extend a bit my question?
Yeah.
If this object moves, suffers, becomes much larger, then the relation to the city or the urban dynamics becomes quite relevant, or they can multiply. I wonder what's the relation between the dialectics of the city and the object.
Yep.
And if there's a connection on these two sexual information.
Yes. I'd have to show you. I don't have a treatise on that, but yes. No, I think that's what would make it interesting, is having not a whole building move, like the Prada transformer necessarily, but pieces of the building that reconfigure, even seasonally, generates a whole other relationship to the city than something that just opens and closes. And I think it should activate an urban response and also bring an urban experience into a building that you couldn't have otherwise. And I think that's what people are doing. I think that's why Liz and Rick are doing what they're doing in the Hudson Yards, is because it lets them have a different relationship to the city. So when it's Fashion Week, it's going to have one, the building's going to show up one way, and when it's not Fashion Week, it's going to show up as an art institution. And that makes it kind of just more vibrant as a civic structure. So I don't think it's so much the spectacle of the movement as what it can do in its context and urbanistically. So yeah, I totally agree.
Could you start to sketch kind of cultural geography of the areas of elaboration or discussion of some reflections? We had yesterday Peter dealing with his experience at MIT. We have the representation today in a certain way parallel or part integrated into the paper, whereas it's not by chance then you move to California, which is not simply, how can I say, there is, I think, also a cultural component in this kind of shift that we decide to do. There is always the reference to Santa Fe and a kind of English background, which is not only what you said today, but kind of other English experience. Then through archaeology and digitally, we have been trying to create some other experience in other areas. Could you start to try to delineate, perhaps not the complete landscape, perhaps not a perfect topography, but at least some points that in your opinion, are interesting in considering as a point of generation of research and
one of the reasons that I love digital technology is it's a little bit of an Esperanto between design fields, and it allows a lot of mistaken communication, but it also opens up a lot of relevance for different fields on others. And one of the things that I see happening, I mentioned Nike this morning, but I mean, that's a company that went from sweatshop, global transportation, to the most fully digital company I'm aware of. I mean, they are like 100% digital in their manufacture, their design, the fuel bands that measure what you're doing, and give, let you customize stuff. I mean, they really jumped in a way I've never seen somebody do so quickly. And every single person I met there, with the exception of the CEO, is trained as an architect, and most of them practice as architects. So from John Hoke, who runs design, to the person that invented Flynet, they're all architects, and they all think about construction, manufacture. They think of a shoe like a building. And it's really incredible how all over the place there's the need for not just an architectural skill set, but architectural knowledge. And I think there's a lot of hotspots for that. But I really think that our field can not only have an impact on other fields, but what we do can have relevance to other fields the more we make those kinds of connections. But I really think a lot of it is through the digital technology, and it's the upside of the monopolization of software tools, because we're using exactly the same tools that everybody else is using. So it's real easy for us to talk the same language as all kinds of other fields, like we used to do, like architects used to do several hundred years ago. But there was a kind of specialization that detached us from a lot of other fields that now is getting lateral again. And I find that really exciting, and I really gravitate to the places where that's happening. But that's a little bit more of a technical landscape than a cultural landscape, but I mean, you find that there's also a cultural impact in those places. The Silicon Valley culture, it's not in the Hollywood entertainment and aerospace culture. It comes out of an approach to the way things get designed and made. So, I mean, that's why I'm out there. I mean, that's why I like it there.
But historically, would you try to help because there are people here that are part of this, say, last 20 years experience. Perhaps the two of you, would you try to raise some point of interest in this kind of evolution of the discussion to arrive to the point that you have described, perhaps the way you mentioned Silicon Valley, it's clear, but we can mention MIT, we can mention whatever. I'd like it perhaps to be interested from your side to define some points, some moments that you feel that will be interesting. Or some people, if you don't want to go so much to the point.
Well, what was going on at Columbia, at the AA, Peter said that SciArc is an extension of that project. I really do think that there was one ingredient missing in that Ivy League mix, which is knowledge of materials. I mean, it was shocking to me when, let's say, the GSD started getting interested in composites. And you would see some composite panel that was clipped into a stainless steel set of clips that was then bolted into a stainless steel subframe that was then attached to a steel structure. And it was like they were fetishizing 75 connections when really anybody that knows anything about composites would just put some 5900 glue on and stick it to the steel and it'd be done. So that knowledge base that came from other industries was missing there. And I really think that a certain development happened and stopped and shifted and restarted where that other missing component was. And that's why I think London, with its film industry and its aerospace industry and its naval industry, Southern California, Washington State, Ancona, certain parts of Italy, Istanbul. I mean, I think it's no accident that that's where all that action is, because that's where those technologies at the scale of the building are getting executed in other fields. And so, I mean, those are, for me, in terms of a cultural landscape, that's where you get the right mix of design, architecture, and let's say contemporary construction. And I don't know where it's happening in Asia. I mean, it's just because I don't know Asia well enough, but I know it's got to be happening somewhere soon.
Oh, Korea, I also thought about Asia.
Yeah.
But I would imagine Korea is starting to.
Yeah, I mean, Istanbul is like the most interesting place around because it's exploding this kind of synergy of this kind of construction and design and also culture. But yeah, I do think you could probably objectively measure a certain mix of components that would be necessary to do a certain kind of architectural innovation. And by the way, like Permastelisa, they're a huge player in this whole thing. And that was just a complete quirky fluke. That was a place with craftsmanship that engaged digital technology that just let them explode in a whole market. But so yeah, craft and tradition and history is probably also useful in all that.
What I get from what you say is that it's not very much important who is doing the design, but it's a combination, if I understand well, of a certain industry, and it's not who is designing, but if certain components are not there, something will never happen.
Well, it's why I get the chills when you see original. It's like my Midwestern mother saying special. In my heart of hearts, I think all this stuff is just inevitable. I mean, I really believe it's just going to happen. I mean, I might be wrong, but I've been through one cycle where what seemed like was a kind of ridiculous foray into composable technologies that would never find their architectural home. I was shocked by how fast it happened. Like, I thought I had more time, frankly, to do my own work. And it's like, what? Like, Peter Brand is doing what? And then all of a sudden it's, SOM is doing what? Like, that's not what SOM does. But then all of a sudden Foster and, I mean, everybody, like, it just took off faster than I ever imagined. I'm sure, I really do believe that this stuff is, like you said, a product of culture, geography, technology. It's definitely a little mix, and you get the mix right, stuff happens. I mean, I'd like to think the agency of individuals has something to do with it, but I actually think it's more just, keeping your eyes open.
I agree. I think it's just about being able to know what elements to put together. And I have the same sense of, at some point, being able to kind of turn around So, but I think that's part of the talent now of the designer, is to be able to identify, as you're describing, hotspots, opportunities, and players, and being able to put these things together to understand what 2 or 3 elements need to be brought together at a specific time. And that's, I think, an important shift in education that really needs to take place as well. As that kind of entrepreneurship, if you will. I mean, it's a kind of entrepreneurial thing.
A lot of architects went to Detroit and Chicago and all these places for exactly the same reason 60, 70 years ago. I mean, who would have gone to Detroit?
Yeah.
I mean, at a certain point, it's like, why aren't you in Detroit? Or why aren't you in Chicago? Like, why are you still in, you know, Stuttgart or wherever it was? So, no, I think it's definitely the cultural geography and technical geography and intellectual geography is all, I mean, that's the missing part of this, and you just look at it in terms of what's the software tool that was in 1995, you miss it. I mean, also that's Montreal, Toronto, and Vancouver were giant players in all this. I mean, every piece of software came from Canada. And I don't know why. We were talking about it last night. I actually don't know what spawned the fact that every entertainment package.
Is he Canadian? There might be a couple of key people. No, Bill Buxton was really important in the SGI in this world.
Well, yeah, that hardware world was all Stanford in the end, but the software was all, I don't know. It's probably why every actor's from Australia. It's, you know, subsidies and culture. Professional sports. You know, I'm sure there was some funny mix that made it all happen in 3 Canadian cities, but it goes to this point of paying attention. That's why it's so, I think it's so important for historians to start to work on this time period, because that's the kind of stuff a historian notices and a designer doesn't. You know, we just noticed the early technology, and historians going to pick up on these larger issues. So.
But it brings back a little bit the conversation outside of the geographical local scale. I was interested in again the trajectory of the presentation from Chicago to this last project. So basically from projects that use projected use geometry to Wright architecture, and that architecture in the plan, for instance, of the Opera House. I mean, the plan of the Opera House describes and also the distribution and the kind of all of the functions that might be recorded by the program of the building itself. So it's the geometry that records the program of the building, and I wonder whether somehow digital technology at the end, and with your emphasis on the surface, might not have drifted the possibility of, let's say, of registering or tracking down the function of a given building from this actual, let's say, the description of the space to the surface itself. In other words, you know, if the plan of the Cardiff Opera is a way to imagine, or maybe it's the most synthetic way of imagining the project itself. On the other hand, the ergonomic studies about how to handle the coffee pot somehow describe how the surface becomes a way to memorize the program without the need of the geometry and the plan itself. So I wonder whether that somehow is sort of a discovery and drift and not so much of an anticipation.
I think pulling the stuff from the 80s and 90s together, it is really funny how everything was procedural. It might have just been spending so much time in Peter's office or something, that let's say the Sears Tower was very procedural, that there was a curved line and a floor, and you start at this end and you just, doink, all the way along, you array those floors. Yeah, the doinking. And then Cardiff, same thing. Took the basin, mirrored it, duplicated it. But again, very procedural. Every one of those things was, like, animated is a wrong term to use, but yeah, procedural operations. So whether it was a computer or not, it was always something which was kind of iteration, step by step. That's something I feel a little bit more is a memory. I mean, I'm sure I still think about that, but yeah, now it's much more, working surfaces, let's say, with more or less information, and not so much a procedural process. So, and again, I think that's the heart of the new parametrics is procedural operations, and hierarchical nested operations where you can do a massing, do a detail, array a detail on the massing, array another set of details on that detail. It's, that's a real procedural type of thinking.
I want to say that the geometry you mentioned at the beginning with this image is in a way, helps you to go towards the procedural, and now you can liberate your, it's the surface you're mentioning now. Something that is opposite. How do I relate the geometry and the procedure to the more surface interest now, and the animation?
The curves and curved surfaces were always there. They were just there as controlling geometry, not construction.
Okay.
So in the church, it was all modeled with big smooth shapes. It's just then beams and columns and facets, were then arrayed across those curved surfaces. Now I would just work with curved surfaces.
I'm trying to understand, to follow up.
Yeah.
Well, I think we can stop here also because tomorrow morning we need to have more energy and come back to all these memories. Thank you, Greg. Very good.